going to start with the 45-degree family so we can make all of the dots where angles with a reference angle of 45 degrees hit the unit circle. And we can label our degrees as 45 degrees, our radians as pi over 4. So again, we're going to try to label things in the same position. So when I go to quadrant 2, if I think of the reference angle as 45 degrees, to figure out this angle is 135 degrees, what I would do is I would say, well, all the way to the negative x-axis would be 180 degrees, minus 45 degrees would give me 135 degrees. In quadrant 3, I would think, well, 180 plus 45 degrees, that will give me 225 degrees. And in quadrant 4, I would think about going all the way around to 360, subtract 45 back, and I would get to 315 degrees. Now, if you're able to think this through in degrees, it's the same process in radians. So if you found 135 degrees, right? We found 135 degrees by doing 180 degrees minus the reference angle of 45 degrees. You could find out what it is in radians if instead of 180 degrees, you think of pi radians, and now instead of subtracting 45, we'd have to subtract pi over 4. But we also have to use some knowledge from the past. How do you subtract fractions? You subtract fractions only if you have a common denominator. Here, I don't have a common denominator, so I'm going to change the pi to be 4 pi divided by 4. Now I have a common denominator. 4 pi divided by 4 minus pi divided by 4. That will give me 3 pi divided by 4. And so 3 pi over 4 in radians is the same as 135 degrees.
All grade 11 students, both English and French, plus their teachers, should be going to the gym now. That's all grade 11 students, both English and French. Please go to the gymnasium, and your teachers should also attend with you.
All right, so I will post this afterwards for the grade 11. Similarly, if we went to quadrant 3, you would do pi plus your reference angle, so it would be 4 pi over 4 plus pi over 4, and you would get 5 pi over 4. And in quadrant 4, all the way around is 2 pi minus pi over 4. 2 pi is the same as 8 pi over 4. So you think 8 pi over 4 minus pi over 4 would give me 7 pi over 4. So for the 45-degree family, we can find the degrees, we can find the radians as well. Now, in the space off to the side in one of the corners, what I'd like you to write is, in order to find the coordinates, we are going to write down a special triangle for 45 degrees. What we're going to do is we're going to make a right-angled triangle, and we're going to label one of the angles as 45 degrees and see what we notice. Now, first of all, if you have a 90-degree triangle and one of the angles is 45, you know that the whole thing adds up to 180 degrees, and you could figure out that this other side is also 45 degrees, which makes this a special triangle. What do you call a triangle where two of the angles are the same? Remember the name of it? Starts with an I. It is an isosceles triangle. And isosceles triangles not only have two angles that are the same, they also have two sides that are the same. So I know that those two sides have to be equal. And trigonometry is powerful because trig ratios, what sine of 45, it doesn't matter how big or how small the triangle is, sine of 45 is always going to be the same answer. When you type in sine of 45 into your calculator, it doesn't say, oh, are you dealing with a big triangle or a little triangle? It says it doesn't matter. It'll give you the same answer every single time. So when we're looking at this special triangle, I can pick any number for this side. As soon as I pick a number for this side, I know this other side is going to be the same. I'm going to pick 1. If I pick 1, then I know this side is 1. If I pick 2, then the other side would be 2. And if I do a squared plus b squared equals c squared now, I would know that this side is the square root of 2. If I had picked 2, then I would have 2, 2, and the square root of 8. Now that I've labeled those sides, I can figure out what sine of 45 degrees is without my calculator. I know that it's the opposite over the hypotenuse. Opposite side is 1, hypotenuse is root 2. And what often happens, just like in grade 11, you would rationalize the denominator by multiplying the top and bottom by the square root of 2. And you would get square root of 2 over 2. So in grade 12, when they ask you what's sine of 45 degrees, you can either write it as 1 over root 2 or as square root of 2 over 2. Same thing with cos of 45 degrees. It'll also be square root of 2 over 2. And tan of 45 degrees, which is opposite over adjacent, 1 over 1, will just be 1. I think the tan is the easiest to see that it really didn't matter how big of triangle you picked. Like if we picked both sides to be 3, can you see the tan would have been 3 over 3, which reduces to 1. So no matter what side length you choose for your special triangle, when you simplify things, you will always get root 2 over 2, root 2 over 2, and 1. And now we can use our big idea, so we wrote it in our legend, for the coordinates. Our big idea from this unit is that the x-coordinate is cos theta, the y-coordinate is sine theta. So in our triangle here, I'm like, oh, cos of 45 degrees is root 2 over 2. Sine of 45 degrees is root 2 over 2. And I can write the coordinates. Then when I move to the other quadrants, the coordinates will have the same values, but now if I go to quadrant 2, my x-coordinate has to be negative. My y-coordinate is still positive. In quadrant 3, my x-coordinate would be negative and my y-coordinate would be negative. And in quadrant 4, my x-coordinate is positive again. And my y-coordinate is negative. And from our special triangle, we can also label, we'll just label tangents separately. Tangent to pi over 4, positive 1. You can also see that tangent of pi over 4 has to be 1 with the big idea. Remember the big idea for tangent is that it's sine theta over cos theta? And if sine theta is my y-coordinate, and cos theta is my x-coordinate, if you have root 2 over 2 divided by root 2 over 2, it's the same number. You're going to get 1. In quadrant 2, tan of 3 pi over 4 is going to be negative 1. You can see that it has to be negative from your cast rule. You can also see that it has to be negative from your big idea. that if I do sine of theta divided by cos of theta, one of them's positive, one of them's negative, I'm going to get a -1 as an answer. Quadrant 3, tan is positive again in quadrant 3, so tan of 5 pi over 4 will be +1. And in quadrant 4, tangent's negative again. Tangent of 7 pi over 4 will be -1. And there's our pi over 4 family. I don't remember who was the last person to answer a question. They might be gone. So we're going to start with Nathan picking the first volunteer. Okay, so I'll say the question first so everybody can think about it. We're going to try to figure out what is cos of 3 pi over 4. Cos of 3 pi over 4. And you're going to pick someone. Liam.
Cos of 3 pi over 4?
Yeah.
Negative square root 2 over 2.
Perfect. So we go to 3 pi over 4. Cos is your x coordinate. Negative square root 2 over 2. What about sine of 7 pi over 4? What are you going to pick? Braden.
Sine negative root 2 over 2.
Negative root 2 over 2. So we go to our y coordinate at 7 pi over 4. And we get negative root 2 over 2. What about sine of 5 pi over 4?
Gotta I guess.
Negative root 2 over 2 again. Perfect. All right. That is our 45-degree found. And we get the coordinates from this special triangle. Next, we go to our 30-degree family. Again, we can mark these coordinates where the 30-degree reference angles all hit the unit circle. In degrees, your reference angle for all of them will be 30 degrees. In radians, your reference angle for all of them will be pi over 6. And I'm going to give you a head start to label the rest of the degrees and the rest of the radians. All right, let's see how you did. 4 degrees did you get? 150 degrees, 210 degrees, and 330 degrees. And for the radians, did you get 5 pi over 6, 7 pi over 6, and 11 pi over 6? And in this space between the 30-degree family and the 60-degree family, we are going to have a special triangle. And it's actually the special triangle for 30 degrees and 60 degrees because if I make a right angled triangle, and I make a special triangle for 30 degrees, when I add up the rest of the angles, the other angle has to be 60 degrees. Now we talked about the special triangle from the first one being isosceles triangle. Other triangles that you've learned about equilateral triangles where all the angles are the same and all the sides are the same. We use that in our definition of the radian, right? To figure out that a radian was 57.3 degrees roughly, a little bit less than 60. Now this triangle has all the angles different, which means all the sides are different. This is like a lot of triangles. In fact, they gave a name for this. This is because these triangles they're not really special in any ways, unfortunately. And the name for not special triangles is scalene. So here we have this triangle, probably feeling not very special, walking down the street, feeling like a not very special triangle, runs into another triangle that looks just like it, and you know how they probably have a little conversation, say hi, yeah, I'm not a special triangle, and the other guy says, yeah, I'm not a special triangle either, and they're like, well, you want to be friends? And they're like, okay, we can be friends because we're both kind of like not special triangles. So if I draw this other not special triangle right beside it, exactly the same, 90 degrees, this is 30 degrees as well, this is 60 degrees, and when they get together, something special. When you put those two not special triangles together, you end up making a big equilateral triangle. And in that big equilateral triangle, since all the angles are 60 degrees, we could say all three big sides have to be the same. And if all three big sides we can choose any number we want. I'm going to choose 2. Because if I choose 2 and 2, this side's 2, but it splits up nicely to 1 and 1. And all of a sudden, we have side lengths for our special triangle. And we can do a squared plus b squared equals c squared again, and get that this length here has to be the square root of 3. And now, we can do sine, cos, and tan of 30 degrees and 60 degrees without our calculator. Look, sine of 30 degrees. Opposite over hypotenuse, 1/2. Cos of 30 degrees. Adjacent over hypotenuse, √3/2. And tan of 30 degrees. Opposite over adjacent would be 1/√3. If you rationalize this, this would be √3/3. And we can also write sine of 60 degrees, √3/2. Cos of 60 degrees, 1/2. And tan of 60 degrees, √3/1. So with one triangle, duplicating it, we can create the special triangle for the 30 degree and the 60 degree family, which then allows us to go up to here and say, I now know the coordinates. Cos of 30 degrees from my special triangle was √3/2. Sine of 30 degrees for my special triangle was 1/√2. And if I have the coordinates in quadrant 1, I have the coordinates in all the quadrants. I just have to think about what's going to be positive and what's going to be negative. So in quadrant 2, the x-coordinate would be negative, the y-coordinate is still positive. In quadrant 3, they'll both be negative. And in quadrant 4, my x-coordinate will be positive and my y-coordinate will be negative. And from my triangle, I can also write what tangent of 30 degrees or pi over 6 would be. Not 1, just wait. Sorry. Tangent of pi over 6 is root 3 over 3. And then using your CAS rule or your big idea, quadrant 2, it'll be negative. Quadrant 3, it's positive again. And in quadrant 4, it's negative again. So where did we end off at? Sine of 150 degrees. Was Gabby the last one? All right, Gabby gets to pick. Sine of 150 degrees. 1/2. Perfect. Cos of 11 pi over 6. Chelsea. Square root of 3 over 2. Sine of 7 pi over 6. Ben.
What?
Sine of 7 pi over 6.
I'm kind of lost.
Okay. So, if we're doing sine of 7 pi over 6, you go to 7 pi over 6, get to the coordinate, and then the big idea from the unit circle says your coordinates are cos, theta, sine theta. So if I want to find sine of 7 pi over 6, I just have to go to my y coordinate at that point, and I would get negative 1/2.
Is this in the lesson from yesterday?
This is in part of the lesson from yesterday and the big ideas from, was that yesterday as well? Probably.
Okay.
So you'll have to catch
Is
up.
that on YouTube
It
yet?
is on YouTube already. Okay. And now we can also do coterminal stuff. So for example, if I asked you what is sine of negative pi over 6, you would have to think, where is negative pi over 6? Negative pi over 6, standard position would start here, go in the opposite direction. Can you see that negative pi over 6 would be coterminal, or end in the same place as 11 pi over 6? So if I asked you what is sine of negative pi over 6, we would be at this coordinate, and you would get negative 1/2. So we can do all sorts of angles. I could even do, what is cos of 17 pi over 6? And you'd be like, there's 17 pi over 6. Well, all the way around once would be 12 pi over 6. I would have to add another 5 pi over 6, so I would find out that 17 pi over 6 is coterminal with 5 pi over 6. And then if I ask what sine of 17 pi over 6, it's going to be positive 1/2. The nice thing about radians is it'll be easy to figure out reference angles. Because 17 pi over 6 has a reference angle of pi over 6. 23 pi over 6 will have a reference angle of pi over 6. But if I go to degrees, right, and I said, what is cos of 570 degrees? It's a little bit harder to tell if that's part of the 30-degree family. But 360 plus 210 gives me 570 degrees. So cos of 570 degrees will be negative root 3 over 2. And our last family, let's draw the dots. This is our 60-degree family in radians, that's pi over 3. And from our special triangle, we already know the coordinates. Cos of 60 degrees was 1/2. sine of 60 degrees was root 3 over 2. And I will give you a head start to finish the degrees, the radians, and the coordinates. Oh, you can even do tan. Tan of pi over 3 is root 3. All right, let's see how you did. Degrees, did you get 120 degrees, 240 degrees, and 300 degrees? In radians, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And for your coordinates, negative 1/2 root 3 over 2, negative 1/2 negative root 3 over 2, and 1/2 negative root 3 over 2. And finally, tangent of 2 pi over 3, negative root 3, tangent of 4 pi over 3, positive root 3, and tangent of 5 pi over 3, negative root 3 again. Cameron, I sent an extra one down this room for you. Same thing, William, I have an extra one of this one for you. next, what we're going to do is we are going to transfer all of this information from the 4 families onto one single piece of paper. And one of the things I recommend is color coding your families. Because I don't know if you started to notice, but the coordinates all stay the same, just positives and negatives change, right? So I have in green, I color coded my 45-degree family. In yellow, I color coded my 60-degree family. And in green, I've color coded, or in blue, sorry, I've color coded my 30-degree family. And what you're going to do, and we're not going to take time to do it right now, but you're going to take all of the information from all of your families and transfer it on to that quiz, including filling out the chart at the bottom. And the chart at the bottom is just the questions I was asking, like, what is sine of pi over 6? You would go to pi over 6, you would look at your y coordinate, it's 1/2. That's how you fill in your chart. What is cos of pi over 4? You'd go to your x coordinate at pi over 4, and you'd fill in root 2 over 2. Now, unlike other quizzes that we have in the class, this is going to be an in-person quiz. And unlike other quizzes, the quiz that we're going to be doing on next week, Wednesday, looks identical to this. It's only one side, though. You don't have to do both sides. Okay? And also what's different about this quiz than any other quiz that we do is this quiz you are required to get 100%. If you don't get 100%, you get 0%. It's either all or nothing. And you have to get everything right without a mistake. Okay? However, you get multiple attempts. So if you don't get it on your first try, you can have as many attempts as you want in 1 week. You have 1 week to get 100%. So you will either get 10 out of 10 on this quiz or 0 out of 10 on this quiz. Now a lot of people get 10 out of 10 on the first try because they start to recognize that really, if you know quadrant 1, all the other ones are the same, right? Reference angles are the same, so they can figure everything out. But inevitably, there's some people who do the whole quiz and miss a negative. Then they have to do the whole thing again. So it's about attention to detail, no mistakes. That'll be next week on Wednesday. Okay? The other thing that we are going to do with all of this information is we are going to transfer all of this information onto a paper plate. So I'm going to give each of you a paper plate, and you are going to take all of the information that you have and put it nicely and neatly on a paper plate. So here's an example of a student. They have made the inside their unit circle. Then on the outside, they have all of their radians in dark purple, all of their degrees in light purple, their coordinates in green, their tangent in teal. It's really easy to see all the information and really easy to get all the information off of it. Here is another example of another student. Which one should I show you? Let's do... I know which one I want to show you next, but I can't find it. No, wait, I won't show you that one next. Next one, oh, here it is. Next one I'm going to show you. This one person has made it look like a spider web. They made all of their radians really big around the outside. Then they put their degrees in the inside here. then their coordinates and tangent all in there, and they even put the digits of pi starting at the top here, 3.14, and they wrote about 300 digits of pi around the outside edge of their circle. There's another one that actually painted a pie on the front of their unit circle, have all the information at different places, nicely organized, clean and easy to get the information off of it. This person decided to separate the 4 quadrants into 4 seasons. Summer, or fall, winter, spring, and summer. And if you look closely on this, there's like leaves and snowflakes. And if you look really closely at the leaves, they've actually attached the leaves, they're made out of cloth, with a sewing machine. They sewed them right on to the unit circle. So at this moment, you're probably thinking, okay, this is a little crazy. Why did these people go to these crazy things on these pie plates? Well, this is an assignment, but it's also a competition. Okay? The competition works as follows. Once everyone has submitted their pie plates, I randomly spread them out. I randomly find teachers that are walking by, and I say, hey, you're a judge. Pick your top favorite based on neatness, creativity, whatever that teacher feels like when they come in. They pick their top 5. If you get a number 1 place, it's worth 5 points. If the teacher picks yours as number 2, it's 4 points. Number 3, 3. Number 4 is 2 points. And if you get a 5th place, that's 1 point. And after I've asked about 7 or 8 teachers, I add up all the points. And the top 3 are going to be winners of the competition. And each of those top 3 get a bonus mark on their next test. So that is the competition. So that's why you get some crazy ones like this, and even this neat one that I showed you at the beginning. On the back side, they had painted a blueberry pie with a piece of pie taken out. Had some other crazy ones. Someone made a working clock once. And I had a bunch of other crazy ones you might have seen around, but I have to start taking things off my walls for painting. So some of those crazy ones are not out right now. Okay, so how do we go about doing this? Well, first of all, we are going to start the activity, so I'm going to give each of you a paper plate. You are given 1 paper plate for free. If you screw things up and need another one, then you have to give a donation. And I give the donation to whatever the next charity that the school is running. Minimum donation of 25 cents. So you screw up. And some people decide, like, this guy decided the spider web one. He didn't like what he was doing at first, and then he cut out another circle and just stapled it on top. Or you don't have to use the pie plate. Some people have made posters. Some people have added the pie plate onto other things. Oh yeah, I do have here. You want to see some bigger crazy ones? I do have a couple. There was this one. You see the pie plate with the moon. And they painted something. The craziest one I have already put in. Someone had made an honorary degree and they put a big medal there, and the medal was the pie plate.
What's the bonus one?
So
Just a single point.
On the test, which ends up being the test is out of 52% on the test. So, but people get crazy. Okay? So, the first thing that we are going to do, got an extra? The first thing that we are going to do is, and stress on carefully, carefully fold it in half. So the way that you carefully fold it in half, because it's stiff and it's not easy to fold, is you attempt to fold it and you try to use your fingers to line it up so the curve is perfect. And once you're holding that tight, you can press it down and it will fold nicely in half. If you're not holding it tight while you press it down, it could shift on you and not fold perfectly in half. So we fold it in half, hold it tight, then press it down on the table, squish it, it'll fold nicely for you in the end. Some people fold it both ways, get a nice crease going for your fold. That is your first fold. The second fold is a little bit more complicated than the first fold. The second fold, same idea. Now you're folding it the other way, but not only are you trying to match up the curve so it doesn't shift, but the first fold has to match up perfectly on both sides so that the fold mark and the fold mark are in the same spot. Then fold it in half again. That should perfectly find the center of your pie plate and create 4 90 degrees and 4 quadrants. Now the rest of the instructions we'll go through, but we won't. And Karen, I sent an extra one down there for you. And I sent an extra one for Liam here. So what we're going to do is we're now going to, right, these folds that you have made your axes family. You can use whatever colors you want. Some people like to make their axes families in black. You know, some people use different colors. So we're going to label our axes family, and then you're going to color code each of your families. So for example, on the spiderweb one, they made their pi over 6 family in red, their pi over 4 family in teal, and their pi over 3 family in orange. So they color coded things. And again, you have whatever you need to make it creative. This one with the 4 seasons, they just did dots around the outside because they didn't want the lines to mess up their picture. It's perfectly fine. You have your own creative license to do what you like. This one drew the lines and color-coded them. Now, when you measure your angles, you know, if you're at home, you can print out a protractor from the internet, or if you have your own protractor, you can measure 30 degrees, measure 45 degrees, measure 60 degrees. The lines will go straight across as you do that, and so you can draw all of your angles correctly, right? Here's one that looks really nice, but they lost some marks because they didn't measure. They made them all equal. And between 0 and 30 degrees is 30 degrees, but between 30 and 45 should only be 15 degrees. So they shouldn't be equally spaced. Looks nice though, when they're all equally spaced. This one, here's another one. Person did a dartboard, and they thought, oh, it looks nicer if they're all equally spaced. Interestingly, both of these ones that are equally spaced were done by the same person. They made very nice ones twice, but lost marks twice for equally spacing them both times that they took the course. Okay, so have each of your colors. Then you are going to put everything that we have on our test, or everything on the 4 families on here. And you should choose some sort of organization so that it's easy to tell and easy to get the information off. So where are you going to put all of your degrees? Maybe you put them all in the same spot. Where are you going to put all of your radians? So that you can tell which things go where. Is it going to be easy to tell which way you should hold your plate? Like this one, as soon as I see this, because they have the axis family huge in radians there, I can hold it, I know it has to be this way right away. Whereas this one, when I grab it, I might have to spin it a couple of times to figure out which way should it go. So it's nice if you can tell right away how you want to find it so that you can get information off of it quickly and easily. So you have to color code it in some way. And then once you've decided on the back, you are going to do a quick little legend. This person just color coded on the back, which family was which color, which things were which color. A little legend on the back. And give your pie plate a creative name. We're going to name our pie plate. This one was named Pie Face. Sometimes people get creative with the names and play on words. So for example, I don't know, this was hard to see the picture on there. Can you see the snake? You know what this one was called? A pie. Very nice, right? Right? So that was a little, oh, look at this, the pie pirouette. Okay. Oh, we got another one here. See if you can figure out the name, the creative name of this one. Anybody have an idea? Octopie. Oh yes. Octopi. We've got, oh, do you know your fish? It is a pike. Northern pike. Spelled. Pike. Sometimes people try to be creative with their name and have fails. There are name fails. This is a great name fail. The sun with planets. This one was called Planets. I would say that's a bit of a name fail. They tried to include pi, but it doesn't work with planets. Planets, maybe a little bit of a name fail. Sometimes the names are just plain, like this person liked purple. They chose 4 different shades of purple to do their pie plate, and they called it the purple pie plate. That's perfectly fine. We've got, oh, does anybody know what this one is? Pumpkin pie. Oh, right? Oh, yeah. Oh, too bad I have some of them. Oh, this one. Making pie a piece of cake. Anyway, so you can have fun. You don't have to, like, this one's named Gary. This is Gary the snail. That's the name of this pie plate. Doesn't have to have pie involved in it. So you have choice of making it creative and making it your own.